Okay, so in this video, we're going to wrap up Unit 1 by looking at projectile motion, or specifically 2D motion. Okay, and we call it 2D motion because our object is going to travel the X and the Y direction, where before it was the X or Y direction. So when it comes to projectile, first we need to define what is a projectile. So a projectile is any object that is thrown, kicked, batted, or otherwise launched in motion, then allowed to follow a path determined slowly by the influence of gravity. Not gravity, but gravity. Okay, so this is very much like free fall. So you go free fall, then projectile motion, because the vertical direction of projectile motion is essentially free fall. So there are going to be a couple assumptions that we make here in AP Physics 1 for projectile motion. One is that air resistance can be ignored, just like we did with free fall. We don't have to worry about the air resistance. And that the acceleration due to gravity is constant and directed downward with a magnitude of g equal to 9.81 meters per second squared. So when you plug that into the equations, though, you need to make sure you include the negative sign, right? Because that downward, right, is our direction, and the magnitude will be the 9.81. Now, one thing to note is that the horizontal and vertical motions are independent of each other. Okay, although the object moves off together in the X and Y directions, one does not affect the other. So the way we think about it is that horizontal motion looks like a ball rolling with a constant velocity, which means there is no acceleration in the X direction. And that the vertical motion will look like the three types, or one of the three types of free fall. So again, it's going to go back to our 9.81 meters per second squared. Now, when it comes down to it in the end, in physics, there's two types of problems. And both these pictures here show that. The first style is what we call a cliff problem, where the initial velocity will only be in the X direction. And then, but as it travels, it will pick up a Y velocity. And the other one is basketball, right? Football, kicking, whatever, is what we call launched at an angle. Okay, so that means we're going to have a VOX component, and then we will have a VOY component if we're launched at an angle. So here we'll talk about the equations real quick. So one thing to remember is that there's no vertical acceleration and only a vertical acceleration. So what that allows us to do, we can rewrite the equations in the X and Y directions, where in the X directions we just simply say the acceleration is 0. So any part that has acceleration, it goes away. So for an object's position, you can simply write using the quadratic equation written in the horizontal and vertical direction. So that quadratic, remember, is x equals xo plus VOT plus 1/2 AT squared. So if I'm going to write this in the X direction, I can eliminate all of anything to do with acceleration. So we get that equation of motion. Right, and in the Y direction, we're going to have to keep it all in place. So we're going to write some more subscripts here. Okay, we're going to keep that in place. We're going to keep the whole equation in place because there may be a time where we have, no velocity initially in the Y direction, but there's going to be times where we have Y initial and velocity. And we're going to keep this, right, part because remember, there is an acceleration in the Y direction where AY is equal to negative 9.81. I'm going to keep writing that just so you can get into your heads what the acceleration is. So in general, an ideally launched projectile or ideal projectile follows a parabolic path regardless of how it was launched. Any projectile's velocity can be determined at any point in time by using the velocity time equations. And so the velocity time equation would be V equals VO plus AT. But the good thing is, right, in the X direction, it's constant velocity because there's no acceleration. And in the Y direction, it's going to be Vy equals VOY plus AT. In fact, we can rewrite these a little bit by plugging in that A is negative 9.81. So this equation becomes y equals y0 plus v0yt minus 4.9 t squared. And this equation will become v0y minus 9.81 t. Okay. Now, if a projectile is launched at an angle, there's an added step, not stop, or added stop, right, of resolving the initial velocity vector into its horizontal and vertical components. If you're not sure what it means by resolving, I have a separate video on vector resolution. And so our initial x component would be VO cosine theta. Our initial y component would be VO sine theta, right? So our initial velocity times the sine of the angle. So these are our equations that we're going to use in all of our projectile motion questions. So let's look at some examples. So we got a skateboarder moving at a constant speed of 1.3 meters per second, releases a ball from the height of 1.25 meters above the ground. Given that the initial x position and the initial y positions are given to us, what are the horizontal and vertical positions at 0.250 and 0.500? Recall that g equals 9.81 meters per second squared. So because I'm looking for position, I'm going to use my two position equations. So that's going to be y0 plus v0yt minus 4.9 t squared. Now, something to note, if an object is being released from some sort of vehicle moving out of, like, essentially just dropped or released at any point in time, it assumes the velocity of the car, okay? So in this case, we have a skateboarder, right? They're going to release this object, and it's going to be released horizontally because they're just going to drop it. And so it's going to follow a path as if it were a cliff-style problem, right? If you go back to the first page or the first little bit of this video, okay? So initially, it's moving the x direction 1.30 meters per second, and the y direction is initially moving 0 meters per second. Right, so here we're going to call that 0. Here, it tells us our x position is 0. Okay, and so I'm going to say x equals VOXT. And so for part A, the horizontal will be 1.30 times 0.250. Okay, and that's going to give me a x position, right? Because we're only looking at the x for this one. 1.3 times 2.50 of 3.25 meters. And now a y position, right, it's going to be 1.25 minus 4.905, right, because I'm doing 9.81, times 0.250 squared. And so because this is falling down, we have to, we know we're going to be below our initial y position. And so that's going to tell me it's going to be at 0.943 meters. Okay, so that's part A. Now part B, we're going to do it. We're going to go out to 0.5 seconds. So again, it's going to be 1.30 times 0.500, or so. Oh, I'm sorry, I messed up the first one. So the first one is 1.3 times 0.250. We're just going to probably move it. Yep. So this is going to be 0.325, and this is going to be 0.65, because by simply just doing, yep, so 0.065 meters, right? So after half a second, after a quarter of a second, that's after half a second. And so we're going to do, now plug in the 0.5 seconds here for the second part. So 1.25 minus 4.905 times 0.5 squared. And you can see we're going to be closer to the ground. Okay, they may add another question here and say, when does it hit the ground? At what time does it hit the ground? You just keep using this equation. Okay, next one we're talking about a golfer trying to go over a 3-meter high tree about 14 meters away. Okay, the ball lands on the green, of course, at the same level from which it was struck. After traveling 17.8 meters, if the ball left the club at an angle of 54 degrees above the horizontal, landed on the green 2.24 seconds later, what was the initial speed? And then the ball passes directly over the tree at 1.76 seconds. How high was the ball at this time? Okay, so we're going to say x equals voxt, right? Because again, I'm going to say my initial position is going to be 0, so I don't have to write that in there. And so I know for my x initial velocity, it's going to be VO cosine theta. And notice they give me all the information that I have, okay? And so all I'm going to do is solve this for VO. So it's going to be x over cosine theta times t. So it tells me I land 17.8 meters away. It leaves my club or the club at cosine 54 and lands 2.24 seconds later. So again, make sure your calculator is in degrees. And so this is going to be fun because I may guess that this calculator is not in degrees. It is not. How do I know? I ended up with a negative answer. So I'm going to go to mode, change back to degrees. And it tells me that my initial velocity is 13.5 meters per second. So that's my answer to part A. How fast did it leave our club? 13.5 meters per second. Now, why do we need that? Because we can write our y-coordinate equation, right, to figure out how high was the ball at 1.76 seconds. So we're going to say y equals 0 plus. Now we can do VOY equals VO sine theta. So we do 13.5 sine 54. And so it's telling me that my y velocity coming off the club is 10.9. And then we're looking at 1.76 seconds at where it hits the tree or goes over the tree. And so we do 10.9 times 1.76 minus 4.905 times 1.76 squared. And it tells us that we are 3.99 meters above the ground, right? Now, sometimes they may say with respect to the tree or something you hit it over. So if it says with respect to the tree, we would just simply subtract out the 3 meter tall tree and find that, you know, we're 0.99 meters above the tree. Okay. All right. And so that concludes Unit 1, talking about kinematics.